All right, this is Unit 3, video number 5. In the previous video, we were talking about electron configurations of neutral atoms. And it's somewhat cumbersome because you have to draw boxes and arrows, and it takes up really a lot of space. Once you get the hang of those, the electron configurations, the orbital diagrams, you can abbreviate them. And every time we learn something new, we will figure out how we can make it as abbreviated as possible. So we can represent the electron configuration without needing arrows or boxes. Instead, we write the energy level, here 1 through 7, followed by the sublevels letter, S, P, D, or F, followed by the number of electrons in that sublevel. The number of electrons in the sublevel is written as a superscript. However, a superscript, it's not an exponent. It looks like an exponent, but it's not an exponent. The noble gases are elements in group 18, the far right column on the periodic table. These elements are chemically inert. It means they don't react with anything. There are very few reactions where noble gases participate. Usually they're off by themselves, doing their own thing and ignoring every other element. Noble gases are the most stable elements on the periodic table, and there's a reason they're stable. It's because the outer energy level is completely filled with electrons. The outer energy level has the necessary amount. It doesn't have any extras that fill up a higher level. It doesn't have holes that need to be filled. It's got everything it needs. So the electron configuration of a noble gas does not change. We can also use the electron configuration of a noble gas to write an abbreviated electron configuration. So we had orbital diagrams, that was our boxes and arrows. The electron configuration eliminates the boxes. The noble gas configuration makes it even more abbreviated. So let's go ahead and look at some examples, and then we'll come back to those pieces. For the element neon, which we have already used, you should have an orbital diagram of neon on the previous page, so I will have you reference that. So we're going to reference the orbital diagram as we do the electron configuration. Remember, the first energy level is 1. The first energy sublevel is S. And if you're looking at your diagram, there is one box and it has 2 arrows. So I'm going to write 2 here, meaning that there are 2 electrons in this sublevel. This is not 1s squared. Please do not refer to it as 1s squared. When we say this out loud, we would just say 1s2. The second energy level begins with the S, and looking at that box, you have 2 electrons there. Also in the second energy level, you have the P sublevel. And for neon, if you're looking at your orbital diagram on the previous page, you see 6 arrows representing 6 electrons. So that's 2p6. Just to double check, remember neon has 10 electrons. So we look at this, there's 2, here's 4, plus 6 is 10. And this is a shorter version of what we talked about for the orbital diagram. When I read this out loud, I would say 1s2, 2s2, 2p6. For oxygen, so you're flipping back to your orbital diagram. It starts off energy level 1, sublevel S. There's 2 arrows in that box. Then energy level 2, sublevel S. There's 2 arrows in that box. Then energy level 2, sublevel P. There are only 4 arrows in this sublevel, representing 4 electrons. So oxygen has 8 electrons when it's neutral. 2 plus 2 is 4, plus 4 is 8. And we're done. And when we're talking about this, we would say 1s2, 2s2, 2p4. Magnesium. Remember, it had 12 electrons. Starts with the 1s. There's 2 arrows in there, 2 electrons. Then 2s. Again, there's 2 electrons. Followed by 2p. We have 6 arrows in 2p, representing 6 electrons. Then we have energy level 3, sublevel S, with 2 arrows, so we have 3s2. So just to double check and make sure that I have 12 electrons, 2 plus 2 is 4, plus 6 is 10, plus 2 more is 12. Silicone, we're talking about 14 electrons. Energy level 1, sublevel S, has 2 electrons. Energy level 2, sublevel S, has 2 electrons. Energy level 2, sublevel P, there's 6 electrons. Level 3, sublevel S, has 2. And then we have 3P, which has 2 arrows representing 2 electrons. Let's make sure these total 14 just to be sure. 2, 4, 10, 12, 14. And we're good. There's a lot of repetition here, and in some ways that's good. As we're learning it, it's nice that they all follow the same pattern. But you get this idea that we wrote a lot of the same letters and numbers over and over. For instance, every single one of these has 1s2, 2s2. A lot of them had 2p6, and a couple of them had 3s2. So these are only smaller atoms too. If we were going to do a large atom like krypton or xenon or radon, this would be a really long electron configuration. And while it is easier than the orbital diagram and takes up less space, it's still going to be a lot of writing. So we have another abbreviated version. Flip back to the previous page. Remember, the electron configuration of a noble gas is not going to change. They're stable because their outer level is completely filled with electrons. So we can use the electron configuration of a noble gas to write an even more abbreviated electron configuration. Here are the basic steps. Use the next smallest noble gas. So we want to figure out what's the next smallest noble gas. So to do this, you're going to look up one period and all the way to the right. So we're going to use the next smallest noble gas, but it's important we need to see the electrons in the outer shell. So here's how we're going to abbreviate these. For neon, we want to find the next smallest noble gas. So we look up one period and all the way to the right, and that would be represented by helium. Helium is the next smallest noble gas. Now, if we put helium in brackets, in this context, this represents the electron configuration of helium. The electron configuration of helium would be 1s2. So we're talking about this right here is helium. So then we need to see the electrons in the outer shell, or the outer energy level, and that would be energy level 2. So 2s2, 2p6. For a smaller atom, it may not be any less work for the noble gas configuration. But for a larger atom, it's going to be very helpful. Here's one thing that you cannot do. So we're talking about neon, and we went up one period and all the way to the right. You might have this temptation to say the noble gas configuration of neon is the electron configuration of neon. And this is not going to work. It needs to show the next smallest noble gas, because we need to see all of the electrons in the outer energy level. And that's why these are here. They are absent from this one. So for oxygen, same idea. I'm going to find oxygen on the periodic table. I'm going to look up one period all the way to the right. Again, that is going to be helium. And so that just abbreviates the 1s2. We still need to see all of the electrons in the outer energy level, which is energy level 2. So 2s2, 2p4. For magnesium, we find magnesium on the periodic table. Its atomic number is 12. It's in group 2. And it's in the third row. It's in the third period. And so we find magnesium and we look up one period and all the way to the right. The next smallest noble gas is neon. So we're going to be able to use neon as our abbreviation. We already have the electron configuration of neon. It's 1s2, 2s2, 2p6, which means that if we use the brackets with neon, we have abbreviated 1s2, 2s2, 2p6. This one's going to save us a lot of writing. So we have the electron configuration of neon, and then the electrons in the outer energy level, which is 3s2. Example 8, find silicon on the periodic table. It's in group 14. Its atomic number is 14, and it's in the third period. So we find it, we look up one period and all the way to the right. The next smallest noble gas is neon. Then we have to represent the electrons in the outer energy level, which is energy level 3. 3s2, 3p2. So here's 10 electrons, 12, 13, 13, excuse me, 10 electrons, 11, 12, 13, 14. And this is going to be a nice abbreviation.